Hello, calculus fans. We're going to talk about applications of double integrals. We'll have a lot of physics applications. Now, our primary application is to compute volumes. Another geometric application is finding areas of surfaces. We'll do that in the next section. For now, we're going to study physics applications. We'll do things like compute mass, electric charge, center of mass, and moments of inertia. So let's start with density and mass. Back in one variable calculus, we were able to use single integrals to compute moments and centers of mass of a thin plate, or a lamina, with constant mass density. Now that we have a double integral, we can consider laminas with variable densities. So you imagine a flat plate that has different thicknesses as you move around the plate. Let's suppose that the lamina occupies some region of the xy plane, and its density, and the density will be measured in mass per unit area, at some point xy is given by rho of xy. So that's not a p, it's a rho, it's a Greek letter. Rho is some continuous function on D. So what this means is that we can think of rho as being the limit of a mass divided by area. This limit is taken as the dimensions of some rectangle approach 0. So here's a picture of a lamina, and then there's some rectangle surrounding the point xy, and the mass density is defined by the mass divided by the area, and then taking a limit as we approach 0. The size of the rectangle approaches 0. So in order to find the total mass of the lamina, first we enclose the region D inside a rectangle, and then we divide that rectangle into subrectangles. And if we need to, we'll consider rho to be 0 outside of D. That way there is no mass outside of D. Let's look at a picture. So you see we have enclosed our region inside a rectangle, and now you're looking at a particular subrectangle. I'm also indicating a sample point. We're going to use that in the development of the double integral that's going to represent the mass. So we've chosen a sample point in this subrectangle, and we do that for every subrectangle. The mass of that portion of the lamina that occupies that subrectangle is approximately rho of xjk star yjk star delta A. So it's the mass density times the area. And delta A is the area of that subrectangle. Then we add up all those masses, we get approximation to the total mass. This is a double Riemann sum. And so we follow the usual game now. If we increase the number of subrectangles, we're going to get the total mass of the lamina as the limit of these approximations. And this is no longer an approximation. We define the mass to be this. So we define the mass to be the limit as the number of subrectangles goes to infinity. And this is simply the definition of the double integral of the density function over D. And in physics, we also consider other types of density that can be treated in the same way. So as an example, you could have an electric charge that's distributed over some region D. Maybe you have some metal plate, and we have a function that gives us the charge density. That's units of charge per unit area. And so now we'll use a function like sigma of xy to indicate the charge density at some point on the lamina. So then the total charge can be computed by doing a double integral of the charge function. So really it's the same application, it's just using a different point of view for what it is that you're measuring. Okay, that's all for now.